Theoretical physics is hiding a massive contradiction right at the core of how the universe works. We have two incredibly successful instruction manuals for reality, and they refuse to talk to each other. The first manual is Albert Einstein's General Relativity. This is the math of the very large. It dictates how gravity steers galaxies and planets, treating space and time as a smooth, continuous, predictable fabric. This visualization illustrates the problem. General relativity is that smooth curve on the left, but on the right is our second manual, quantum mechanics. Down at the scale of atoms, reality is governed by discrete probability clouds, making erratic, microscopic jumps. Every time we test general relativity by measuring starlight bending around a sun, it passes. Every time we test quantum mechanics by building a microchip or a laser, it passes. Within their own size domains, the math works. The trouble is their mutual exclusivity. The universe cannot be a smooth, continuous fabric and a jittery, pixelated grid at the exact same time. If you try to force them together by applying the smooth equations of general relativity to a subatomic object, the math shatters. You get strings of infinities, producing complete gibberish instead of usable physics. Normally, you can keep the large and the small separate, but nature forces them together in two specific places: the immense density of the Big Bang and the crushing core of black holes. Here, immense gravity and microscopic size overlap, demanding a single set of rules. To solve this, we need what physicists call a theory of everything. But there is a catch. As established by the philosopher Karl Popper, for a theory to be considered science, it must be falsifiable. We have to be able to run an experiment that could prove it wrong. We are caught between a logical necessity and a physical wall. We need one theory to explain these extremes, but we can't reach the energy levels required to see if it's actually correct. Our leading candidate, string theory, replaces 3D point particles with tiny, one-dimensional strings vibrating across 11 dimensions. Conversely, loop quantum gravity focuses entirely on space itself, quantizing the fabric of the universe into tiny, interlocking loops. This logarithmic scale maps the true scale of the problem. Both of these theories operate down at the Planck scale, that is 10 to the -35th meters. If an atom were the size of the entire visible universe, the Planck length would be the size of an average tree. Here is our engineering crisis. To build a particle accelerator capable of smashing atoms hard enough to see physics at the Planck scale, the machine would need to be roughly the size of the Milky Way galaxy. Because we cannot directly observe these strings or loops, vocal critics label these theories not even wrong. If you can never test it, you are doing beautiful math, not provable science. Physicists are attempting an end run around this limitation. You do not necessarily need to see the quantum strings or loops directly if you can spot their macroscopic footprints. In this schematic of an atom interferometer at CERN, you can see how researchers hunt for these footprints. The device splits an atomic wave packet down two physical paths before recombining them. If spacetime is made of jittery quantum fluctuations at the Planck scale, the recombined wave pattern won't be crisp. It picks up a microscopic fuzziness. It starts to blur. By looking for these microscopic anomalies in the lab, researchers are trying to squeeze information out of the Planck scale without a galaxy-sized machine. It's one of the few practical windows into the origin of gravity. But what if our inability to prove a theory of everything isn't an engineering failure? What if it is a law of logic? In 1931, a mathematician named Kurt Gödel published a paper that challenged the limits of human knowledge. If we look at this Venn diagram, we can visualize Gödel's incompleteness theorem. He demonstrated that any sufficiently complex mathematical system will always contain true statements that simply cannot be proven from within the system itself. Since science assumes the universe follows logical mathematical laws, many physicists argue that reality behaves like a formal mathematical system. If it does, then it's subject to the same internal limits as arithmetic, leaving some truths about the universe forever beyond formal proof. The act of observation creates a paradox. We are humans inside the universe attempting to define it. When a system tries to define itself, it creates an infinite loop. This suggests that the final theory of everything will never be a neat, finished equation we can print on a t-shirt. Every time we zoom in, we will find new discoveries, requiring new axioms. This mathematical incompleteness means the universe will always hold mysteries. It is the structural guarantee that the human pursuit of knowledge will never end.